There is a date on the Navy's calendar that says more than any speech could. In October 2026, the service plans at-sea demonstrations for a new medium unmanned surface vessel marketplace, and 7 companies have already been selected to compete in that test window. That single decision carries the pressure of something much larger than one procurement event. It suggests a Navy that no longer believes time is a luxury. The question in this episode is not simply whether America can build more ships. It is whether the United States can build naval power fast enough for the kind of ocean contest now taking shape. And in the opening move, the Navy is not leading with a destroyer keel or a carrier overhaul. It is leading with unmanned vessels, prototype competition, and a promise that success will be rewarded quickly. Picture the scene in practical fleet terms. A gray sea rolling under a hard morning sky. A support ship holds steady while deck crews move with practice speed around a launch station. Lines are checked, consoles come alive, antennas turn, and a compact unmanned craft is eased into the water. Nearby, sailors at a control position watch screens rather than a helm. On another deck, maintainers crouch beside access panels, tracing cables, checking connectors, confirming that logistics and engineering are aligned before the vessel ever clears the wake. This is not a futuristic fantasy. It is the visible shape of a Navy trying to shorten the distance between concept and fleet use. The service calls it a marketplace approach. That matters. A marketplace is not the old image of a single winner locked into a long and careful path, while years pass in paperwork, redesign, protest, and delay. The structure here points toward prototype competition, at-sea demonstration, and a success incentive tied to performance. The official announcement puts that incentive at $15 million. In plain terms, the Navy is trying to push risk outward, bring multiple designs forward at once, and learn in the water instead of only on paper. That does not mean the problem is solved. It means the Navy has begun acting as if the old pace is no longer acceptable. For years, American naval discussion has been dominated by the familiar symbols of sea power: carriers, submarines, destroyers, amphibious ships, the industrial strain of maintaining them, and the strategic fear that replacement is too slow and too expensive. But the drone deadline changes the emphasis. If unmanned vessels can be fielded in numbers, adapted quickly, and integrated with the fleet, then naval growth no longer depends only on waiting for the next major warship to arrive from a crowded yard. That is why this opening matters. It is not about replacing every traditional ship. It is about building enough useful maritime presence, sensing capacity, and operational mass to close a dangerous time gap. The logic is already appearing across the fleet. In the high north, during Arctic Century 2026, the United States and Norway used unmanned systems in a bilateral exercise tied to maritime domain awareness, mine countermeasures, and the protection of undersea infrastructure. Those are not abstract missions. They are concrete tasks in hard water among Allied forces under conditions where distance, weather, and uncertainty magnify every weakness in response time. An unmanned vessel in that setting is not just a gadget. It is another set of eyes, another sensor path, another way to reach a problem without immediately placing a crew in the first position of risk. Visualize that beat as fleet footage rather than theory. A cold deck, slick with spray. Crew members in flotation gear move carefully around a launch cradle. A small vessel drops into steel-colored water, while a rigid inflatable circles nearby. In a control room, operators track routes and data feeds as the sea state shifts beyond the windows. Farther below, communications gear hums in a compartment lit by instrument glow. At the edge of the frame, logistics is always moving. Batteries, spares, cases, cables, sealed containers, the unnoticed labor that turns an exercise into repeatable practice. The strategic meaning is simple. The Navy is not waiting for a distant future to think about unmanned operations. It is already exercising them with allies in conditions that test endurance, coordination, and trust. That trend is reinforced by organization. In April 2026, the Navy established Unmanned Surface Vessel Squadron 7. Its stated role centers on robotic autonomous systems and operations in bandwidth-limited or denied environments. That phrase is important because it removes the comforting assumption that unmanned systems will always operate in perfect communications conditions. A fleet that depends on constant clean connectivity is a fleet with a built-in weakness. A fleet that prepares for degraded links is preparing for something closer to reality. So the opening chapter is not about a single contract notice floating in isolation. It is about an institutional pattern. The Navy is buying differently, exercising differently, and organizing differently at the same time. Then widen the frame again. RIMPAC 2026 is set to bring together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. Even without adding a single speculative claim, those numbers alone tell us something about the scale of coalition warfighting the Pacific still demands. The modern fleet does not operate alone, and it does not operate in small numbers. Any American answer to naval urgency has to fit inside that coalition-sized maritime reality. Imagine the visual sequence. A flight deck at first light as rotor wash scatters spray. A destroyer cutting through open water with replenishment gear rigged nearby. Sailors at a combat information center watch layered tracks move across displays. On another ship, handlers guide palletized cargo across the deck because logistics motion is as decisive as missile counts. Overhead, aircraft pass low and vanish into haze. The image is not just power. It is complexity. A Navy is a system of systems, and every attempt to speed construction has to answer that complexity without pretending it away. This is where the unmanned push becomes more than a technology story. According to Defense Analysis reporting, the Navy aims to deploy thousands of smaller unmanned surface vessels in the Indo-Pacific by 2030, while also pursuing more than 30 medium unmanned surface vessels over time. That reporting should be treated carefully because it is analysis rather than a simple official commitment. But even as a reported direction, it reveals the scale of the ambition. The Navy is not talking about a few experimental hulls tucked into demonstration units. It is talking about mass. Mass is the key word. Senior naval leadership has described a future Hedge force built around robotic autonomous systems and what has been called risk-worthy mass rather than a one-size-fits-all fleet. That idea cuts straight to the heart of the build rate question. If every problem must be answered by a limited number of exquisite, high-cost ships, then naval expansion remains slow, almost by definition. If some missions can be carried by more numerous, more adaptable unmanned systems, then the Navy gains another way to distribute risk, presence, and sensing power across the map. But aspiration alone does not put steel in the water. The requirement picture matters too. Defense Analysis reporting on the prototype phase describes a medium unmanned surface vessel concept shaped around approximately 2,500 nautical miles of range, 25 knots of speed, operation in Sea State 4, and a payload of roughly 25 metric tons with containerized payload options. Even with cautious attribution, those figures help explain what kind of vessel the Navy appears to want. Not a toy, not a disposable skiff, but a platform substantial enough to travel, carry mission equipment, and operate in meaningful sea conditions. That is the cold, open tension in its clearest form. The Navy's deadline is not just to build something new. It is to prove that new things can be built, tested, integrated, and scaled before strategic time runs out. And behind every promising concept stands the old American question of industry. The broader 2026 shipbuilding debate links unmanned systems to a high-low fleet mix and to modular, distributed shipbuilding ideas meant to ease industrial bottlenecks. That connection matters because naval power is never just about design. It is about yards, suppliers, labor, throughput, maintenance capacity, and the discipline to keep a production line moving. An unmanned marketplace can accelerate learning, but it still has to connect to a real industrial base that can deliver hulls, payload modules, support equipment, and sustainment without collapsing under its own constraints. So when we ask whether America can still build a navy fast enough, we should hear two clocks ticking at once. One clock belongs to strategy, exercises in the Arctic, coalition operations in the Pacific, the expanding need for maritime awareness and undersea infrastructure protection, and the sheer size of the theater where presence must be maintained. The other clock belongs to production, prototypes, competitions, demonstrations, modular builds, and the search for methods that can move faster than the traditions they are trying to supplement. On screen, the chapter should end where it began, with motion. A small unmanned craft carving across a choppy surface. A camera on deck catching sailors securing gear after launch. Operators in a command space leaning over data feeds as the vessel tracks out beyond the ship. Forklifts and pallet carts move equipment along a pier. A crane swings a container into place. A crew chief checks a station one final time before turning away. None of it is dramatic in the theatrical sense. That is exactly why it works. Naval power is built out of repeated acts of preparation, movement, adaptation, and proof. October 2026 is only a test window. It is not victory. It is not even certainty. But it is evidence that the Navy understands the urgency now pressing on every discussion of ships, yards, and fleet design. The drone deadline is really a decision deadline. Either the United States finds ways to turn maritime ideas into usable capacity faster than before, or it enters the next decade still arguing about speed while the ocean keeps moving. That is where our story starts. Not with a finished answer, but with 7 selected companies, a planned at-sea demonstration, and a Navy racing to discover whether a faster path to fleet mass is still within reach. The old fleet does not disappear when a new ocean arrives. It keeps watch, keeps station, keeps moving fuel, aircraft parts, food, sailors, and orders across distances so large they distort every easy promise made on shore. That is the first reality to hold in mind. When the Navy talks about a faster path to mass, it is not speaking into a vacuum. It is speaking from the decks of ships already at sea, from command rooms already crowded with tracks and radios, and from a logistics system that never gets to pause while the future is being designed. Picture the scene in safe, familiar detail. Early light on a gray flight deck, non-skid wet with spray. A lookout scanning a restless horizon through salt haze. A line handler in a cranial and float coat checking movement at the rail. Below, in a machinery space, watchstanders monitor gauges and vibration while the ship holds course through a moderate sea state. In combat information spaces, operators sit before consoles, measuring distance not in miles of highway, but in long arcs of water and time. Every decision, every sortie, every transfer of fuel or stores has to survive the ocean before it can prove itself in strategy papers. That is why the Navy's current turn toward unmanned systems matters. It is not a fashion change. It is an attempt to answer a basic problem. The ocean has grown more crowded, more watched, and more demanding, while traditional fleet capacity remains difficult to expand quickly. The service is now searching for ways to add mass without waiting for a single perfect design to solve everything. Senior Navy leadership has described a future force that is not built on a one-size-fits-all model, but on a hedge force shaped by robotic and autonomous systems in what they call risk-worthy mass. The phrase matters because it accepts something the old fleet learned long ago. Presence has value, numbers have value, and not every mission requires the same level of cost, crew, or platform complexity. The old fleet understands concentration. The new ocean demands distribution. That shift can already be seen in how the Navy is organizing itself. In April 2026, Unmanned Surface Vessel Squadron 7 was established with a mission centered on robotic autonomous systems, including operation in bandwidth-limited or denied environments. That detail is easy to overlook, but it is one of the most serious signals in the story. It means the Navy is not treating unmanned vessels as demonstration pieces for perfect conditions. It is preparing for a harsher reality, one in which communications can be constrained, interrupted, or contested. A future fleet that depends entirely on pristine connectivity is not a fleet suited to a difficult ocean. A fleet that plans for limited bandwidth is a fleet trying to become operationally credible. You can imagine the visual rhythm of that transition. A conventional warship, steady on course, wake stretching white behind the stern. Then a cut to a smaller, unmanned craft being craned, launched, or recovered in controlled sequence. Crew at a control station. Antennas, monitors, gloved hands over checklists. A rigid hull boat crossing chop. A mission bay with equipment secured for sea. Not a science fiction Navy replacing sailors overnight, but a real Navy, adding layers to what it can sense, where it can go, and how much risk it can distribute across the water. That is also why exercises matter so much in this chapter. In May 2026, during Arctic Century with Norway, the Navy launched high-tech unmanned systems in a bilateral setting tied to mine countermeasures, maritime domain awareness, and the protection of undersea infrastructure. This is not abstract experimentation. It places unmanned systems in the cold logic of Allied operations, in a region where weather, distance, and infrastructure all sharpen the stakes. The High North is not a forgiving test tank. It is a place of cold decks, shifting visibility, rough water, and long support lines. If unmanned systems can contribute there, in cooperation with an ally, then the Navy is learning something useful about how these tools may extend awareness and distribute effort without asking every mission to be carried by a large crewed ship alone. The visual language is important. A steel deck rimed with cold moisture. A crew in heavy gear guiding a launch with practiced hand signals. Dark water under low light. A remote control station inside a ship where operators monitor a small craft moving beyond the hull's immediate reach. A sonar or mission planning display glowing in a dim compartment. A helicopter view of a vessel cutting through a harsh northern sea. Even without sensitive details, the message is clear. The ocean is not getting simpler, and the fleet is adapting where it can. Then the scale widens again. RIMPAC 2026 brings together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. That is not just a number set for a press release. It is a reminder that the American fleet does not operate alone, and that the future force has to fit coalition realities as much as national ones. Interoperability, missile proficiency, anti-submarine warfare, and mine clearance all point to a common truth. The next fleet will not be judged only by whether a single platform performs well in isolation. It will be judged by whether the whole force can function together, across domains, across partners, and across a maritime environment crowded with tasks. In that setting, the old fleet meets the new ocean every hour. A destroyer or amphibious ship may still provide command presence, endurance, and layered capability. But around it, the Navy is increasingly interested in adding smaller, more numerous systems that can scout, sense, relay, screen, or carry modular payloads into the wider fight. Defense Analysis reporting this spring described a Navy ambition to deploy thousands of smaller unmanned surface vessels in the Indo-Pacific by 2030, with more than 30 medium unmanned surface vessels also in the picture. That reporting should be treated as reporting, not as an official guarantee. But even as a directional indicator, it shows the scale of the change under discussion. The Navy is no longer thinking about unmanned systems as rare attachments to a few experiments. It is thinking in terms of larger numbers and persistent integration. And integration always returns to the hard question: what kind of vessel, built how, for what mission, and delivered how fast? That is where the medium, unmanned surface vessel marketplace effort enters the frame with unusual clarity. In late May 2026, the Navy announced 7 companies selected for at-sea demonstrations planned for October 2026. The structure includes a success incentive worth up to $15 million. The significance is not just that 7 companies were selected. It is that the Navy is trying to learn through direct competition at sea and to transfer some risk away from a slower, more conventional acquisition path. Instead of waiting for a single long cycle to sort theory from performance, the service is pushing prototypes toward the water and asking them to prove themselves in the element that matters. That approach fits the new ocean better than a paper fleet ever could. The sea is an unforgiving editor. It checks propulsion, range, control, stability, and payload ideas without concern for PowerPoint confidence. Defense Analysis reporting on the prototype phase has described requirements around 2,500 nautical miles of range, speeds around 25 knots, operation in Sea State 4, and a payload near 25 metric tons, with room for containerized payloads. Again, those details come through reporting rather than official specification in this prompts ledger, so they should be understood as reported indicators. Even so, they reveal the shape of the ambition. The Navy is not merely asking for a floating sensor toy. It is exploring a vessel large enough to matter, fast enough to integrate, and modular enough to adapt. Imagine the footage that would carry this idea cleanly. A medium craft underway with spray breaking at the bow. Stabilized shots from a beam showing hull motion in working seas. A deck section with mounted equipment or containerized mission space. Control room screens watched by a small operations team. Sailors or civilian technicians moving through pre-sail checks. A replenishment evolution on a larger ship. Pallets in motion, forklifts or cranes handling stores pierside, fuel hoses secured, inventory crossing from shore to ship to mission. Because procurement speed is only one side of naval speed. The other side is whether the support chain can keep pace once a design leaves the brochure and enters fleet life. This is where the industrial base enters the chapter, not as a slogan, but as a pressure point. The 2026 shipbuilding debate has linked unmanned systems to a broader high-low mix and to ideas of modular, distributed shipbuilding, while also acknowledging industrial bottlenecks. That pairing is essential. It is easy to say that smaller, more modular systems can be built faster. It is harder to prove that yards, suppliers, integration teams, software workflows, and sustainment networks can all accelerate together. The old fleet was shaped by large platforms, long lead times, and concentrated expertise. The new ocean is pushing toward distributed construction, faster iteration, and platforms that may be more numerous, more modular, and less individually central than the ships that defined earlier eras. But nothing in naval history suggests that transition will be painless. Old habits have infrastructure behind them. Existing ships have crews, training pipelines, doctrine, maintenance routines, and command traditions built over years. New systems arrive with promise, but also with questions. How are they maintained at scale? How are they controlled when bandwidth is limited? How are payloads swapped and sustained? How do commanders trust them enough to incorporate them into real plans? How do allied navies understand them, train with them, and operate alongside them? The ocean is new in the sense that threats, surveillance, and timing pressures have changed, yet it is still the same saltwater judge, and it will expose weak seams in any rushed transition. So Chapter 2 is not a story of replacement. It is a story of encounter. The old fleet brings endurance, command experience, and the visible discipline of ships that have carried American naval power across decades. The new ocean brings colder calculations, wider surveillance, longer distances, harder timelines, and a demand for more distributed presence than a traditional force can easily generate by itself. Between them stands a navy experimenting in public view, organizing new squadrons, testing unmanned systems with allies, framing a future of risk-worthy mass, and inviting 7 companies to prove, on the water, whether faster fleet growth can become more than a procurement hope. On deck, the sailors still lean into the wind. In control rooms, operators still track the sea one contact at a time. In the background, logistics still moves relentlessly. Stores loaded, equipment checked, maintenance logged, sea states judged, routes adjusted. The future does not arrive by replacing that labor with a slogan. It arrives, if it arrives at all, by meeting those old realities honestly. And that is why the ocean now matters more than the argument. Because by October, when those at-sea demonstrations begin, the Navy will not be testing an abstract idea. It will be testing whether a legacy fleet can teach a new architecture how to survive in motion, whether distributed systems can stand up to real water and real command demands, whether industrial ambition can cross the gap into operational usefulness, whether the old fleet, facing a new ocean, can still become something larger than itself, fast enough to matter. The old fleet cannot wait for a perfect answer. It has to stand watch while a new layer of naval power is assembled beside it, tested against weather, distance, interference, and command strain. That is where the idea of a hedge force enters the picture. Not as a replacement fantasy, and not as a slogan, but as a practical attempt to add risk-worthy mass to a fleet that already knows how hard the ocean is. Senior Navy leadership has described a future force that does not rely on one single class of ship or one single template for naval power. The emphasis is shifting toward robotic and autonomous systems, toward a broader mix of platforms, and toward a force that can absorb risk in ways the traditional fleet cannot always afford. The central point is not elegance, it is depth. It is the ability to put more hulls, more sensors, more decoys, more payloads, and more persistence into contested water without requiring every mission to rest on the same limited number of exquisite ships. On screen, that idea should feel physical before it feels theoretical. Start with a gray sea under a low sky. Show a destroyer riding a steady swell. Flight decks slick with spray. Sailors moving along, marked lines in cranials and float coats. Cut to boots on steel ladders, a hand on a sound-powered phone, radar repeaters glowing in a darkened watch space, then widen again to the open water because the scale matters. A hedge force is born from a simple fact. The ocean is too large, and the demands placed on the fleet are too constant for a small number of major combatants to do every job alone. That does not mean the Navy is abandoning the large ship. It means the large ship may need company. The old model concentrated enormous value in a limited set of platforms, each carrying great capability and great strategic importance. That model still matters. Carrier strike groups, submarines, and large surface combatants remain central to the way naval power is projected and sustained. But the emerging argument is that they must be surrounded by something more distributed, more numerous, and in some cases, more expendable. Not disposable in the careless sense. expendable in the operational sense, able to take on missions where risk is expected, where contact may be brief, where loss cannot automatically mean strategic shock. The term hedge force carries a revealing tension inside it. A hedge is not a clean bet on one future. It is protection against uncertainty. It is an admission that the Navy may need several answers at once. One answer is still the high-end fleet. Another is a lower-cost layer of autonomous and unmanned systems that can extend presence, complicate targeting, widen surveillance, and create more options for commanders. If one part of the future arrives slower than expected, the other may still buy time. If one concept underperforms, another may still hold the line. In that sense, the hedge force is not just about technology, it is about strategic insurance. The Navy's current moves reflect that logic. In late May 2026, it announced 7 companies selected for a medium unmanned surface vessel marketplace effort, with at-sea demonstrations planned and a success incentive attached to the program. That matters because it suggests a procurement path designed to move through competition and demonstration, rather than waiting for a single fully settled design before momentum begins. Instead of pretending that uncertainty can be eliminated on paper, the service is pushing prototypes toward the water and asking performance to sort ambition from reality. Visually, this is where the chapter can shift from doctrine to machinery. Show a workboat wake crossing the frame. Show an unmanned craft alongside a pier, hull lines clean and unfamiliar. Technicians checking fittings, laptops open on a folding table, deck crew stepping around tie-down points and cable runs. Cut to antennas against a white sky, a compact bridge console, hands fitting connectors into place, an equipment case rolling across non-skid. Keep it grounded in motion and preparation. The hedge force is not an abstract debate in a conference hall. It is a series of systems that have to launch, recover, connect, survive sea state, and remain useful when the neat conditions of a test day give way to the disorder of operations. Reporting on the prototype effort has described performance expectations that point to what this middle layer is supposed to do: meaningful range, useful speed, payload capacity, and the ability to carry modular systems rather than one permanently fixed mission. Those details matter less as promises than as indicators of intent. The Navy is not searching only for a remote-controlled boat. It is searching for a platform that can move through real operational distance, carry enough mission weight to matter, and fit into a distributed architecture rather than a standalone experiment. And the hedge force does not stop at one vessel type. The broader vision reaches across robotic and autonomous systems in several domains. Some of these systems are meant to sense, some to relay, some to deceive, some to strike, some to help defend against other unmanned threats. The point is to create a thicker battle space, one where presence is no longer measured only by the number of large gray hulls visible above the horizon. A future fleet may project power through layers: crewed ships, unmanned surface craft, undersea systems, aviation, and networks linking them under conditions that may be degraded, contested, or denied. That last phrase matters because it is already shaping organization as well as procurement. In April 2026, Unmanned Surface Vessel Squadron 7 was established with a focus on operating robotic autonomous systems in bandwidth-limited or denied environments. That is a quiet but important detail. It suggests the Navy is moving past the assumption that unmanned systems will always enjoy clean communications and constant oversight. The real world at sea is noisier than that. Links break. Weather interferes. Distance stretches timing. Adversaries jam, spoof, and watch. A hedge force that only works with perfect bandwidth is not a hedge at all. It is a lab condition. So the Navy is not only buying craft, it is building habits, commands, watchstanding patterns, and operational expectations around them. On screen, that should be shown through people as much as hardware. A sailor at a remote control station. A supervisor leaning over a tactical display. A team in a command room tracking symbols across a map while another crew works lines on deck. Show coffee cups near keyboards, grease pencils on plexiglass, a headset lifted and set back down. The automation story still runs through human attention. Even the most distributed system must be assigned, monitored, interpreted, and integrated into the larger rhythm of naval decision-making. Exercises offer another clue to what this layer is meant to become. In May 2026, the Navy described unmanned systems used during Arctic Sentry with Norway for mine countermeasures, maritime domain awareness, and the protection of undersea infrastructure. That combination is revealing. It points to a force that is not limited to one dramatic mission set. It can be part of routine surveillance, part of alliance operations, part of defensive screening, part of the quiet but crucial work of understanding what is happening in cold, difficult water. The High North is not a forgiving place for fragile ideas. If systems are being pushed there, the message is clear. The Navy wants these tools measured against operational conditions, not just procurement theory. This is where the Hedge force becomes more than a cost argument. It becomes a geography argument. The ocean gives no discount for optimism. Distances in the Pacific and the Arctic remain what they are, no matter how efficient a briefing slide may look on shore. A fleet spread across those distances needs more than power. It needs coverage. More eyes, more nodes. More platforms that can be sent forward without consuming the full attention and risk budget of major combatants. Defense Analysis Reporting has framed this future in very ambitious terms, including plans for thousands of smaller unmanned surface vessels in the Indo-Pacific by 2030, alongside a smaller number of larger unmanned vessels integrated with carrier strike groups. Even treated cautiously, that reporting captures the scale of what some planners believe will be necessary. The phrase risk-worthy mass helps explain why. Mass alone is not enough. The fleet has had numbers before, and numbers can be hollow if they are fragile, disconnected, or operationally irrelevant. Risk-worthy mass means quantity that can still function under pressure. Systems numerous enough to widen the problem for an adversary, but credible enough to remain useful when conditions deteriorate. In practical terms, that could mean more scouting, more deception, more distributed payload carriage, more persistence around choke points, more support to mine warfare, more support to maritime awareness, and more ways to force an opponent to spend time and attention sorting signal from noise. Yet the Hedge force also carries its own warning. A distributed fleet can fail in distributed ways. A larger number of systems means a larger demand for maintenance, software support, launch and recovery procedures, operator training, repair concepts, and logistics discipline. More nodes mean more things to fuel, transport, inspect, update, and account for. Even an unmanned vessel still belongs to a chain of labor. It needs parts, technicians, test cycles, communications planning, mission packages, and some secure way to tie its output back into the fleet's decision structure. That is why this chapter should never drift into the easy fantasy that autonomy cancels logistics. It does not. It relocates logistics. Show pallets moving across a pier. Show forklifts, tie-down chains, cases marked for electronics handling, hoses snaked across deck plating, a crane lifting equipment aboard. Show sailors checking manifests, a small boat rocking against fenders, a rigid hull crossing a choppy harbor, and then cut to a replenishment ship underway, because the old fleet is still the muscle that carries the new one into place. The Hedge force does not float above the existing Navy. It rides inside its support structure. This is also where the industrial story begins to reconnect with operations. Debate around the 2026 shipbuilding plan has linked unmanned systems to a broader high-low fleet concept and to a more modular industrial approach. That framing matters because it suggests the Navy is not only asking what kind of ships it wants, but also what kind of production and adaptation system it needs. If traditional shipbuilding remains burdened by bottlenecks, delays, and a narrow set of choices, then unmanned and modular systems may offer one path to widen capacity. Not a miracle path, not an instant one, but a path that may allow more components, more payload flexibility, and more distributed construction logic than the legacy model alone can provide. Still, none of this guarantees success. A hedge force can be announced faster than it can be proven. It can be funded in slices, tested in phases, and praised in speeches long before it carries steady operational weight. The Navy knows this. That is why the demonstrations matter. That is why squadron formation matters. That is why exercises with allies matter. Each is a way of asking whether this new layer can survive contact with real tasks. Can it carry enough of the burden to be worth the complexity it introduces? Can it stay coherent when bandwidth shrinks? Can it help commanders see farther, distribute risk better, and stretch presence across a wider ocean? In the chapter with controlled motion, a camera looking aft over a working wake, a small unmanned craft rising and falling in the chop, red lighting in a control space, a sailor adjusting a headset, a navigation display shifting as tracks update, then back outside, cranes, piers, hulls, antenna masts, a slow line of ships waiting at the edge of weather. The hedge force is not the fleet of the future replacing the fleet of the present. It is the attempt to give the present fleet more depth before time runs out. A second line forming while the first is already at sea. A naval wager that mass, distribution, and autonomy can be assembled quickly enough to matter, and disciplined enough to endure the water that will judge them. What emerges here is not simply a new vessel program. It is a different way of trying to buy time. The Navy's medium unmanned surface vessel marketplace is a wager that speed can come not only from better engineering, but from a different procurement rhythm. In late May 2026, the Navy announced that 7 companies had been selected for marketplace at-sea demonstrations. A success incentive of $15 million was attached to that effort, with testing set for October 2026. Even in dry acquisition language, the shape of the idea is visible. The service is not waiting for one perfect blueprint to descend from a long chain of paperwork. It is putting several contenders into the water and asking the sea, the operators, and the mission to begin sorting the answers. That is why this chapter matters. The marketplace bet is not just about what these craft are. It is about how quickly a fleet under pressure can discover what is good enough to scale, what survives contact with salt water and command friction, and what fails before it becomes a larger mistake. The old pattern of naval procurement has often aimed for certainty before volume. This approach leans closer to a contest of proof. Prototype first, demonstrate at sea, reward performance, move risk forward into testing rather than hiding it behind years of slow confidence. For a naval audience, that is a serious shift. A warship is not a software patch. A vessel has to move through sea state, hold its systems together, communicate when the spectrum is crowded, and remain useful when the elegant assumptions of a briefing room begin to break down. So the marketplace idea is not a shortcut past reality. It is an attempt to meet reality earlier. The test is whether that change produces speed with discipline rather than speed alone. Visually, this is where the story should stay grounded. Open on a gray hull line at dawn, low clouds over the water, a deck crew moving methodically around tie-down points and antennas. A medium unmanned craft rides alongside a support ship in moderate chop. Close on, gloved hands securing lines, a console boot sequence, a radar display, washing green across a darkened workstation. Cut to a camera looking aft over a wet deck as spray kicks up along the hull and the horizon rolls slightly under a pale sky. This is not the future as a sketch, it is machinery entering a working fleet. The point of the marketplace is not merely to buy unmanned vessels. It is to discover whether the Navy can create a layer of distributed naval mass faster than it can build traditional capacity alone. Defense reporting around the prototype effort described a demanding profile for these craft: substantial range, meaningful speed, operation in Sea State 4, and room for containerized payloads. If those parameters hold in practice, they hint at a vessel that is not a toy and not a harbor novelty. It is meant to travel, endure, carry mission equipment, and plug into a wider operational design. The concept is not about replacing every manned warship. It is about adding another set of tools that can be moved, risked, and multiplied differently. That matters because naval pressure is measured in distance as much as danger. A fleet stretched across the Pacific or the Arctic does not merely need more exquisite ships, it needs more presence, more sensing, more options between a destroyer and an absence. The leadership language around a future Hedge force has reflected that logic, robotic and autonomous systems, risk-worthy mass, a fleet design that does not ask one ship type to solve every problem. The phrase matters because it captures the emotional center of this effort. A Hedge force is not a parade concept, it is an insurance layer, something you build because you do not trust time to be generous. From there, the marketplace bet begins to connect to operations already visible at sea. In May 2026, the Navy described unmanned systems used during a bilateral exercise with Norway in Arctic Sentry 2026. Those systems supported missions tied to mine countermeasures, maritime domain awareness, and protection of undersea infrastructure. The details are important because they move unmanned vessels out of abstraction. Here, they are not presented as futuristic mascots sailing in isolation. They are part of a cold water allied exercise in a geography shaped by distance, weather, and infrastructure vulnerability. That is precisely the kind of setting where distributed systems either justify their promise or expose their weaknesses. Picture the footage here in a colder palette. A launch in a northern fjord, dark water, snow lingering on distant slopes. A rigid hull boat passes across frame while a smaller unmanned craft is lowered and released. The deck is slick. Crew members work in flotation gear and cranials, breath visible in the morning air. A command room view follows. Headset operators, a feed from an unmanned system, a cursor tracing a patrol pattern over a chart. Then back outside, where the sea is less cinematic than demanding, and the vessel has to prove it can still move, sense, and report. The fleet is also reorganizing itself around this reality. In April 2026, Unmanned Surface Vessel Squadron 7 was established with a mission built around operating robotic autonomous systems in bandwidth-limited or denied environments. That single phrase is a hard check against fantasy. Bandwidth-limited. Denied. In other words, these systems are being prepared for the real conditions of modern naval conflict, where links are strained, disrupted, or broken. The Navy is not just buying craft. It is standing up organizations meant to operate them when communications are imperfect and when neat remote control assumptions may not hold. This is where the marketplace approach becomes more than acquisition theater. If there is a squadron meant to use these systems under contested conditions, then the prototypes must be measured against that operational truth. Can they keep functioning when the network is thin? Can they maintain useful behavior when control is less direct? Can they fit into crews, watch bills, maintenance cycles, launch procedures, and recovery drills that already strain busy ships and shore units? A marketplace demonstration that ignores those questions is just a waterborne trade show. A meaningful one begins to show whether these vessels can belong to the fleet rather than merely visit it. The wider exercise calendar reinforces the same point. RIMPAC 2026 is set to bring together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. That scale matters because coalition operations reveal what brochures cannot. They test interoperability, procedures, timing, language, and command habits across a force that is large enough to generate friction naturally. If unmanned systems are to become part of serious maritime operations, they must eventually live inside that crowded geometry. Not as a separate novelty lane, but as one more moving part in missile drills, anti-submarine work, mine clearance, and the broader logic of naval teamwork. So the marketplace bet sits at the intersection of procurement and coalition reality. Can the Navy buy faster without buying blindly? Can it field new systems quickly enough that they matter before the strategic window narrows further? And can those systems do more than perform a scripted demo? The sea is a stern auditor. So is a multinational exercise. So is a command team already overloaded with tracks, logistics, maintenance demands, and weather calls. There is also the industrial question beneath all of this. Reporting around the 2026 shipbuilding debate has tied unmanned systems to a broader high-low fleet idea and to a modular distributed industrial strategy. That matters because no marketplace can save a fleet if the production base behind it cannot respond. The promise of a distributed unmanned layer depends not only on clever hulls or attractive test footage, but on whether modules can be built, fitted, maintained, and replaced without the same bottlenecks that haunt more traditional shipbuilding. The marketplace, then, is also a probe into industry. It asks which designs can move from prototype to production with the least friction and the most adaptability. That is why containerized payloads matter so much in the concept. A modular vessel is not valuable merely because it exists in numbers. It becomes strategically valuable when its mission package can change with need, when yards and suppliers can support it without heroic improvisation, and when logistics teams can move parts, systems, and repairs through a real network of depots, piers, trucks, cranes, and crews. In visual terms, this chapter should show that motion too. Forklifts crossing a pier, a container module being guided into place, sailors checking lash points, a crane cable under tension, pallets moving below a hangar roof, a logistics officer tracking serial numbers on a tablet while the vessel waits nearby, quiet and purposeful. This is the less glamorous side of naval acceleration, but it may be the decisive one. A fleet does not scale on concepts alone. It scales through stores, maintenance, transport, training, and repeatable processes that still work after the novelty has worn off. The marketplace bet only succeeds if the supply motion behind it is as real as the prototype sprint in front of it. And beyond industry sits the theater problem. Defense reporting has suggested plans for thousands of smaller unmanned surface vessels in the Indo-Pacific by 2030, alongside more than 30 medium unmanned surface vessels. Even treated cautiously, that reported scale tells us what kind of ambition is in view. Not a handful of experimental craft, a distributed presence measured in large numbers. A maritime layer meant to stretch across enormous water, to complicate targeting, extend sensing, and thicken the fleet's options. Whether those numbers are achieved is a separate question, but the fact that such scale is being discussed tells us the marketplace is not a side project. It is one entry point into a much larger attempt to change naval mass. So Chapter 4 lands on a simple truth. The marketplace bet is not elegant because it is tidy. It is compelling because it admits urgency. The Navy appears to understand that the old fleet must remain on station while something new is built beside it. Not someday, now. Several companies, several designs, at-sea proof, success incentives, squadrons standing up, allied exercises in cold water, coalition operations on the calendar, industrial arguments shifting toward modularity and distributed output. The wager is that this can become more than a procurement experiment, that it can become a working second line. Not a perfect answer, but a practical one. A layer of naval power formed in parallel with the fleet already at sea, disciplined by weather, distance, logistics, and command strain. In the end, the marketplace is trying to do something very old in naval history with tools that are very new. It is trying to turn urgency into seaworthy strength before time and the ocean make the choice for it. If these boats are meant to matter, then the question is no longer how quickly they can be selected on paper. The question is what work they must actually perform once they leave the demonstration lane and enter the fleet. That is where urgency meets reality. A medium unmanned surface vessel is not useful simply because it is unmanned, modular, or comparatively fast to acquire. It becomes useful only when it can take on real maritime tasks that fit the Navy's wider problem, covering more ocean, carrying more sensors and payloads forward, and doing so in environments where manpower, risk, distance, and time all work against a conventional answer. That is why the mission matters more than the slogan. The Navy's recent moves suggest it is not chasing unmanned craft as a novelty. It is trying to build a practical layer in a larger force. Official announcements and fleet statements describe robotic and autonomous systems operating in distributed formations, including in bandwidth-limited or denied environments. That tells us something important. These boats are not being imagined only as remote-controlled extras trailing behind crewed warships in perfect communications. They are being shaped for a harder world, one where the sea is crowded, the distances are punishing, and the network may not always cooperate. In visual terms, this chapter lives far from the ceremonial image of a fleet review. The useful footage is more workmanlike. Dawn over a gray sea. A low, unmanned hull rising and falling in a moderate swell. Salt spray crossing the camera lens. A small operations team at consoles, not in panic, but in routine concentration. Hands on keyboards. A watchstander tracking a moving symbol across a tactical display. Deck crews securing equipment. Connectors being checked. Hatches shut. A crane or davit in motion as support gear is moved aboard. Forklifts carrying pallets through a logistics space. Fuel hoses, line handling. Containers staged on a pier. This is the texture of what these boats must actually do. They have to fit into the daily machinery of naval work. One of the clearest clues comes from how the Navy and its partners are already using unmanned systems in exercises. In May 2026, during Arctic Sentry with Norway, the Navy described unmanned surface and undersea systems supporting mine countermeasures, undersea infrastructure protection, and maritime domain awareness. Those are not abstract ambitions. They are concrete categories of naval labor. They tell us that unmanned vessels are being asked to sense, patrol, watch, relay, and support operations in difficult waters alongside allies. In that setting, the value of an unmanned surface craft is not theatrical independence. It is persistence, positioning, and useful presence in places where the fleet needs more eyes and more options. Mine countermeasures alone helps explain the logic. Few naval tasks are more necessary, more methodical, or more dangerous in the wrong waters. A manned ship can do that work, but every mile into a contested or uncertain area carries cost and risk. An unmanned vessel supporting such work changes the geometry. It can move sensors forward. It can help extend awareness across a wider box of water. It can operate as part of a layered team that includes other unmanned systems and crewed ships farther back. The point is not that one boat solves the mine problem by itself. The point is that it helps the fleet do careful, repetitive, high-value work without always putting larger, more complex manned assets in the first position. The same is true for maritime domain awareness. That phrase can sound bloodless until you imagine what it means in practice. It means knowing what is moving on the water, what is lingering where it should not, what pattern has changed, what contact merits attention, and what sea space requires another look. It means a vessel that can hold station, transit deliberately, or remain on task long enough to be useful while feeding into a larger operational picture. For a fleet stretched across enormous distances, that matters. The ocean defeats anyone who tries to watch it with too few holes. An unmanned layer is one answer to that old problem. The Navy's establishment of Unmanned Surface Vessel Squadron 7 sharpens the picture further. The official statement described the squadron as focused on operating robotic autonomous systems in distributed formations, including when bandwidth is limited or denied. That is a revealing standard. It implies these vessels must do more than carry equipment. They must behave predictably inside a command structure that cannot depend on perfect, uninterrupted links. In footage, that means command room screens, voice circuits, route planning, watch rotations, and operators managing uncertainty with procedure rather than drama. It means a vessel that can continue its assigned role when the network thins, then rejoin the wider picture without collapsing the mission. That kind of resilience changes what doing the job really means. A useful unmanned surface vessel is not merely a platform with a motor and an antenna. It must be able to carry a task across time and space with enough reliability that commanders can include it in real planning. If it is sent to extend sensing, escort a pattern of movement, support mine work, or help maintain a surveillance line, it must arrive, remain functional, and contribute in a way the rest of the force can trust. Reliability becomes operational substance. Endurance becomes mission time. Stability in rougher water becomes sensor usefulness rather than brochure language. Defense reporting on the prototype phase gives a sense of the practical requirements being discussed: roughly 2,500 nautical miles of range, around 25 knots, operation in Sea State 4, and about a 25 metric ton payload. Even treated cautiously as reported requirements rather than official final guarantees, those figures matter because they describe the intended job. This is not a harbor toy and not a disposable one-way craft. It is something meant to move with purpose over meaningful distance, carry a real mission package, and stay useful in water conditions that are common enough to matter. That points toward a vessel meant for actual fleet employment, not just demonstration day optimism. And once you think in those terms, the payload question becomes central. The reported emphasis on containerized payloads is especially telling. A modular payload is a way of deciding that one hull should not be trapped inside a single use forever. One mission set may emphasize sensing. Another may support communications or relay. Another may contribute to mine warfare tasks or broader maritime surveillance. The precise combinations will vary, but the strategic idea is clear enough. If shipyards and the fleet can standardize portions of the platform while changing the useful package it carries, then the Navy gains options without waiting for an entirely different class of vessel every time the mission changes. That modular logic also fits a broader naval argument now being made around high-low force mix and distributed systems. Reporting on the 2026 shipbuilding debate frames unmanned systems as part of a wider effort to build a more varied fleet and ease some industrial bottlenecks through modular approaches. Senior Navy leadership has also described a future force shaped less by one-size-fits-all thinking and more by what has been called risk-worthy mass, supported by robotic and autonomous systems. Put plainly, These boats are expected to do enough real work that the fleet can preserve exquisite, expensive manned ships for the tasks only they can perform, while still putting more capability into more places. That does not make the missions simple. In fact, it makes them more demanding. If a medium unmanned surface vessel is part of a larger operational pattern, then it must integrate with crewed formations, coalition exercise schedules, maintenance cycles, launch and recovery concepts, and the daily practicalities of naval logistics. This is where the imagery should stay grounded. Not hero shots alone, but side angles of a vessel tied up alongside a pier. Sailors checking fittings, portable equipment rolled across non-skid decks, a support boat circling in choppy water, a team in cranials and float coats moving carefully around mounted hardware, a plotting display in a dim space aboard a command ship, a logistics manifest clipped to a board, fork pockets on a container, the hum of generators, motion without spectacle. These vessels must be easy enough to move, support, reload, and retask that the fleet will actually use them under pressure. RIMPAC 2026 offers a broader frame for that requirement. The official announcement describes an exercise bringing together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. In an environment like that, interoperability is not a talking point. It is a daily necessity. Any unmanned vessel that hopes to matter in such a coalition context must contribute to a common rhythm of operations. It must be understandable to commanders, supportable by the force around it, and useful in exercises that involve missile proficiency, anti-submarine warfare, mine clearance, and the disciplined coordination of many different assets. A boat that works only in isolation is not answering the actual naval problem. It has to fit into the choreography of a combined fleet. This is also why speed of procurement by itself is not the true measure. The Navy's marketplace approach, with its at-sea demonstrations and a success incentive of up to $15 million for companies that meet the standard in the October 2026 test window, is clearly designed to move faster than a traditional, slower path. But the things being bought are not PowerPoint slides. They are supposed to become working instruments. The demonstrations therefore stand in for a harder question: can these vessels perform the routine, repeated, useful labor of sea power? Can they stand watch, carry payloads, support distributed operations, and remain viable when communications are imperfect and the sea is doing what the sea always does? The answer will not be found in one dramatic trial. It will be found in accumulation, in whether crews trust the systems enough to build them into plans, in whether commanders see them as a burden or as relief, in whether maintainers can keep them available, in whether modular payload ideas translate into faster adaptation instead of new layers of confusion, in whether a vessel launched for a demonstration becomes a dependable member of a larger force package. And that returns us to the essential point. What these boats must actually do is not replace the fleet. It is to make the fleet more present, more distributed, more informed, and more resilient across vast water. They must patrol without ceremony, sense without exaggeration, integrate without friction, and endure long enough to matter. They must help cover the distance between strategic ambition and the finite number of crewed ships the Navy can put to sea. If they can do that, then the marketplace is not merely buying prototypes. It is buying time, presence, and a little more working room on a very large ocean. Out in the high north, the argument for unmanned naval systems stops being theoretical very quickly. In a cold sea, under a low gray sky, there is no room for abstract procurement language. A hull either holds its station or it does not. A crew either sees what it needs to see or it does not. A force either covers enough water to notice danger early or it accepts that something important may go unseen. That is where this chapter settles in, because the undersea problem is not only about submarines, It is also about mines, cables, sensors, infrastructure, choke points, and the vast amount of dark water that must be watched without warning and without pause. During Arctic Century 2026, the United States Navy and Norway used unmanned systems in a bilateral exercise built around intelligence, surveillance, and reconnaissance, mine countermeasures, undersea infrastructure protection, and maritime domain awareness. That matters because it places unmanned craft in a real operational frame. Not a concept sketch, not a conference slide. A working problem set in a demanding environment with an ally that knows these waters well. The point was not simply to launch interesting machines. The point was to see whether those machines could contribute to the slow, disciplined work of sensing, searching, checking, and holding awareness over a difficult maritime space. Picture the footage in practical terms. A small naval craft rides a cold chop beneath a pale horizon. Deck crew in float coats and helmets secure gear against the wind. A compact unmanned surface vessel is craned or slid into the water with careful hand signals and deliberate timing between swells. Nearby, operators at a control station watch feeds, maps, and system health indicators. No dramatic music is required. The scene tells its own story. Modern sea power is not only missiles and flight decks. It is also the patient movement of logistics, batteries, links, launch cradles, antennas, and trained people who can turn a machine into presence. The Arctic is unforgiving to that kind of work. Sea state, cold, distance, and communications friction all press against the neat promises of new technology. That is exactly why this environment matters. If an unmanned system is going to help a navy in the real world, it has to do more than survive a demonstration close to shore on a calm day. It must contribute in places where bandwidth may be limited, weather changes quickly, and the tactical picture is never complete. The exercise with Norway gave the Navy a chance to frame unmanned operations around those realities. Mine countermeasures, awareness of activity around undersea infrastructure, and the larger challenge of knowing what is happening beneath and across the surface before a crisis opens wide. That challenge is growing because the ocean is crowded with things that matter and difficult to guard all at once. Undersea infrastructure does not defend itself. Cables, routes, approaches, and critical seabed spaces cannot be watched by a finite number of crewed ships alone. A destroyer is powerful, but it is also expensive, occupied, and never numerous enough to sit everywhere at once. This is where the logic of distributed, unmanned systems becomes easier to understand. They are not a magical replacement for crewed warships. They are a way to widen the fleet's reach, to fill in observation gaps, and to keep more eyes and sensors on more water for longer periods than the traditional force can manage by itself. That wider reach is one reason the Navy has also been reorganizing around the problem. In April 2026, Unmanned Surface Vessel Squadron 7 was established with a focus on operating robotic autonomous systems in bandwidth-limited or denied environments. That language is important. It suggests a force that does not assume perfect connectivity. In a briefing room, that sounds like doctrine. On the water, it means something more basic. It means the Navy understands that an unmanned craft which only works when every signal is clean and every relay is available is not yet a dependable fleet tool. Any system sent into a contested or remote environment must carry enough autonomy, resilience, and operational discipline to remain useful when communications degrade. So imagine another set of visuals. Inside a compact command room, screens glow in cool light. Watchstanders track contacts, route lines, and environmental data. A supervisor leans over a console, headset on, speaking in measured phrases while another sailor checks a checklist on a clipboard or tablet. Back on deck, tie-downs snap in the wind, a camera mast turns, and spray moves across painted metal. In a logistics bay, Cases of support equipment are shifted into place, charging units checked, connectors sealed, spares counted. This is the texture of the unmanned fleet that matters most. Not sleek renderings, but workflow. Not slogans, but sustainment. Not the machine by itself, but the team, the doctrine, and the repetition required to keep that machine useful at sea. Arctic Sentry also points to a deeper truth about the undersea problem. Much of undersea warfare and protection is about persistence rather than spectacle. Mine countermeasures are patient work. Maritime domain awareness is patient work. Monitoring the status of an area near critical infrastructure is patient work. These missions reward coverage, endurance, and repetition. They reward the ability to send a craft forward, gather information, return it to a command team, and then do it again. They also reward interoperability because no Navy works alone in every theater that matters. In the High North especially, alliance operations are not a decorative feature. They are the operating condition. That is why a bilateral exercise with Norway has outsized importance. It suggests the Navy is testing unmanned systems not just as isolated American assets, but as tools that have to fit within coalition patterns of operation. Shared awareness, compatible procedures, and mutual confidence are part of the capability. A machine that performs well but does not integrate cleanly into Allied maritime operations is only partly successful. The same is true for unmanned systems at a larger scale. RIMPAC 2026, with 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft, provides a reminder of what maritime coalition warfare actually looks like. Many platforms, many commanders, many specialties, and a relentless demand for interoperability across anti-submarine warfare, mine clearance, and broader fleet operations. Seen in that larger context, the unmanned push begins to look less like a side project and more like a practical response to mass and geography. Defense analysis reporting has described Navy plans to deploy thousands of smaller unmanned surface vessels in the Indo-Pacific by 2030, alongside a force of medium unmanned surface vessels. Even when treated carefully as analysis rather than official certainty, the direction is plain enough. The Navy is searching for ways to create more coverage with fewer demands on scarce crewed ships. It is also trying to build what senior leaders have described as a hedge force, shaped by risk-worthy mass and robotic autonomous systems rather than a one-size-fits-all fleet design. The Arctic version of that idea may be especially revealing. In cold northern waters, the value of extra presence is obvious, but so are the constraints. Distance stretches every support plan. Weather punishes small errors. Communications may be unreliable. Operating windows narrow. All of that makes the undersea problem a severe test case. If unmanned systems can contribute there, even in bounded ways, they offer more than novelty. They offer a method for extending awareness around places where a Navy cannot afford blindness. That does not mean every requirement is already solved. Defense analysis reporting on prototype medium unmanned surface vessel requirements has pointed to expectations around range, speed, and payload, including the ability to carry containerized systems. Those figures help explain what the Navy seems to want from this class, not a toy, and not merely a remote camera boat, but a platform substantial enough to travel, carry useful mission equipment, and join real fleet patterns. Yet even a capable vessel is only one layer of the answer. The harder question is whether industry, doctrine, training, and sustainment can move at the same speed as the operational demand. That is where this chapter reconnects with the larger shipbuilding story. The 2026 debate over the fleet is not just about hull counts. It is about a high-low mix, modular thinking, and industrial bottlenecks. Unmanned systems fit that debate because they promise a different kind of scale. In theory, modular distributed shipbuilding can produce useful capacity faster than relying only on a handful of traditional yards and exquisite ships. In practice, the Navy still has to prove that prototypes can mature into durable fleet assets, that operators can trust them, and that support chains can sustain them without collapsing under complexity. So the cold water lesson is a sober one. America does not solve the naval buildup problem simply by selecting companies, announcing squadrons, or describing future concepts. It solves part of the problem by turning those ideas into working presence in the places where presence is thin and risk is growing. Arctic Sentry shows what that looks like at the beginning. Unmanned systems launched into a real Allied exercise, tasked against missions that demand patience, coverage, and undersea awareness. Deck crews working in the wind. Operators studying a feed instead of a brochure. Command rooms translating machine output into maritime judgment. Logistics teams keeping small systems moving so that larger ships do not have to do every job themselves. If these vessels are to matter, this is the standard they must meet. They must help the fleet watch more sea, check more approaches, and guard more of what lies beneath the surface. They must function when the environment is cold, the communications are imperfect, and the mission is monotonous enough to test every weak point in the system. They must fit inside Allied operations and real naval routines. And they must do all this not as a substitute for sea power, but as a force multiplier for a Navy that still has too few crewed hulls for the scale of the oceans it is expected to manage. In that sense, the undersea problem is also a shipbuilding problem. It asks whether the Navy can create enough useful maritime mass, quickly enough to reduce dangerous gaps in awareness and response. The answer will not come from one exercise, one squadron, or one prototype round. But in the Arctic, you can already see the shape of the test. It is not glamorous, it is watch-standing, launch handling, sensor coverage, and endurance in cold water. It is the long discipline of keeping sentries where the ocean is dark, the infrastructure is vulnerable, and the next warning may arrive from somewhere below. And so, the question changes. It is no longer only whether America can build more ships in time. It is whether America can build a different kind of fleet quickly enough, a fleet that mixes large warships with many smaller unmanned systems, and does so before the demands of deterrence outrun the pace of production. On paper, the appeal is obvious. A hybrid fleet promises presence without requiring every mission to be carried by a destroyer, cruiser, or submarine. It suggests a force that can spread sensors wider, patrol longer, and absorb more risk at the edge. In official Navy language, and in the wider shipbuilding debate, this is tied to a broader high-low mix, with unmanned systems reaching across the maritime battlespace as part of a more distributed design. The idea is not to replace the crewed fleet overnight. It is to give that fleet more reach, more mass, and more options. But ideas only matter if they can be built, fielded, and sustained. That is where the argument becomes hard. A hybrid fleet is not just a concept slide with arrows moving across an ocean map. It is hull fabrication, modular payloads, launch and recovery drills, remote control links, watchstanding, maintenance schedules, spare parts, and training pipelines. It is the ordinary burden of turning an attractive theory into something that can leave the pier on schedule and stay useful at sea. The Navy's recent moves suggest that it understands this problem. In late May 2026, the service announced that 7 companies had been selected for the medium unmanned surface vessel marketplace at sea demonstrations. That matters because it shows a push beyond abstract discussion and into comparative testing. Rather than betting everything on one answer too early, the Navy is opening a competitive lane and using demonstrations to learn which designs can actually perform. The same announcement tied that process to a success incentive and an October 2026 test window. That is not the language of a distant dream. It is the language of a service trying to compress learning into a faster cycle. Visually, this chapter lives in that gap between design and deployment. You can see it in footage of a gray hull cutting through a moderate sea, not a glamorous warship profile, but a workmanlike vessel judged by steadiness, wake pattern, and deck behavior. On another beat, the camera rides low along a wet deck where tie-down points, container fittings, and cable runs matter more than outward drama. Crew members move carefully along the rail, checking connections, watching sea state, reading motion in the deck under their boots. In a command space, operators sit before flat panel displays, hands resting near controls, scanning tracks and system health windows. This is what speed really looks like in naval procurement, not slogans: repetition, testing, and correction. Reporting on the prototype phase has described requirements around range, speed, sea state tolerance, and payload capacity, including a vessel able to travel roughly 2,500 nautical miles, make about 25 knots, operate in sea state 4, and carry a roughly 25 metric ton payload with containerized mission packages. Those figures come through defense analysis reporting rather than a formal official specification in the ledger, so they should be understood as reported requirements rather than immutable truths. But even treated cautiously, they reveal the scale of the ambition. The Navy is not asking for a toy. It is asking for a craft that can move useful payloads over operationally relevant distances in real ocean conditions. And that gets to the heart of the hybrid fleet argument. America does not need unmanned vessels merely to exist. It needs them to contribute. They must be able to act as sensors, extend awareness, support mine countermeasures, and integrate with larger naval formations in a way that reduces strain on scarce crewed ships. If they cannot survive routine weather, if they cannot carry practical payloads, if they cannot be sustained forward, then they do not solve the production problem. They only create a second problem beside it. The Navy's own operational framing points toward that larger purpose. During Arctic Century 2026 with Norway, official reporting showed unmanned systems being used for maritime domain awareness, mine countermeasures, and protection of undersea infrastructure. That is important because it places unmanned systems in an environment where conditions are unforgiving and the mission set is concrete. In imagery, the scene is not futuristic fantasy. A launch crew works in cold weather gear beside a small craft at the edge of a steel deck. The sea is dark and uneven. A crane or davit moves with deliberate care. In another shot, a compact unmanned vessel rides away from the host platform, its wake bright against a flat northern light. Inside a control room, sailors track feeds, watch position data, and coordinate with allied partners. The value of the system is not theatrical. It is patient coverage in places where constant crewed presence is expensive and difficult. That same logic scales outward. If an unmanned system can help patrol infrastructure, support mine warfare, or widen awareness in the high north, it can also fit into the broader demand for distributed naval presence elsewhere. The Pacific Fleet's announcement for RIMPAC 2026 described a major coalition exercise involving 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. Even without adding any unsupported claim, that number alone tells you the environment a future hybrid fleet must enter. It will not operate in a vacuum. It will have to work inside crowded coalition spaces with many participating navies, many command relationships, and many tactical demands. A hybrid fleet built quickly but integrated poorly would only add friction. That is one reason organization matters as much as procurement. In April 2026, the Navy established Unmanned Surface Vessel Squadron 7 with an official emphasis on operating robotic autonomous systems in bandwidth-limited or denied environments. That phrase deserves attention. It means the service is not assuming perfect connectivity. It is planning for the kind of contested environment in which a hybrid fleet would actually have to function. A vessel that only works when communications are easy is not solving a wartime problem. It is solving a peacetime demonstration. So can America build this hybrid fleet fast enough? The most honest answer is that it may be able to accelerate pieces of it faster than it can expand the traditional fleet, but only if the industrial and organizational effort stays disciplined. The attraction of smaller unmanned craft is that they can, in theory, be built in greater numbers and through more modular methods than a major combatant. The 2026 shipbuilding debate, as reflected in the source ledger, links unmanned systems to a modular and distributed industrial-based strategy. That is a meaningful clue. It suggests that speed will not come from waiting for a few giant yards to do everything. It will come from spreading work, standardizing components, and making payloads and platforms less dependent on one narrow production path. Defense analysis reporting has gone even further, describing plans to deploy thousands of smaller unmanned surface vessels to the Indo-Pacific by 2030, alongside more than 30 medium unmanned surface vessels. That reporting should be treated as reporting, not as official certainty. But it captures the scale of the aspiration. The Navy is thinking in terms of mass, not boutique experimentation. Senior Navy leadership has also described a future hedge force built around risk-worthy mass and robotic autonomous systems rather than a one-size-fits-all fleet. That framing matters because it explains the strategic logic behind the hybrid approach. A fleet made only of exquisite, scarce platforms may remain powerful, but it is difficult to enlarge quickly and expensive to expose. A hedge force implies another layer, one that can thicken presence, absorb danger, and complicate an adversary's picture without requiring every task to be done by the most precious ships in the inventory. Still, the clock does not stop for doctrine. To build fast enough, America must do more than announce programs. It must move from selected companies to reliable demonstrations, from prototypes to fielded units, from fielded units to crews and commands that know how to use them, and from usage to sustained logistics. In footage, that means less fascination with the launch moment and more attention to everything after it. Technicians swapping modules in a pier-side work area. Sailors checking connectors in spray and wind. A forklift moving palletized equipment across a logistics apron. Fuel hoses snaked along the deck. Operators in a dim control space tracking multiple craft while a larger ship holds station nearby. That is the real test. A hybrid fleet will not arrive all at once, and it will not be judged by rhetoric. It will be judged by whether these systems can be built in numbers, integrated with the fleet, sustained in rough conditions, and trusted when bandwidth shrinks and distance grows. If America can do that, then the hybrid fleet may become the fastest path to more naval mass. If it cannot, then the concept will remain promising but incomplete. Another clever answer slowed by the unforgiving pace of reality at sea. That is where the map grows wider. A navy does not fight alone in the Pacific, and it does not learn the future of war by staring only at its own shipyards. It learns by sailing with partners, by moving data across many commands, by testing whether crewed ships, aircraft, and unmanned systems can operate as one force instead of many separate pieces. The question is not simply how many hulls America can launch. The deeper question is whether those hulls and the machines that will sail beside them can join a battle network strong enough to matter when the sea becomes crowded, contested, and uncertain. In that sense, the future fleet is not only a shipbuilding story. It is also an interoperability story. It is a story about whether allied navies can share enough awareness, enough timing, and enough trust to turn scattered formations into a combined maritime system. The steel matters, the engines matter, the yards matter. But just as important is the invisible architecture that binds ships, aircraft, operators, and sensors into a usable picture before a crisis becomes a fight. That is why exercises matter so much. They are not ceremonial gatherings. They are not only public demonstrations of flags and friendship, they are working laboratories at sea. They reveal whether a Navy's new ideas survive contact with weather, fatigue, distance, maintenance demands, and real operational friction. They show whether command teams can process information quickly enough, whether logistics chains can keep motion alive, and whether allied crews can coordinate under pressure without slowing each other down. RIMPAC remains one of the clearest examples of that test. In 2026, the exercise brings together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. That scale matters by itself. It means crowded sea lanes, full flight decks, busy watch stations, and command rooms tracking a moving picture across air, surface, and subsurface space. It also means something more important. It means the future fleet is being imagined not as a single national armada, but as a coalition instrument that must operate across languages, procedures, platforms, and doctrines. On screen, that kind of exercise is not abstract. A wide dawn shot shows gray hulls moving in formation through a long Pacific swell, flight decks washed in early light. A helicopter lifts from a destroyer stern, while deck crews crouch low in colored jerseys, hands signaling through rotor wash. Below, in a combat information center, watchstanders lean over glowing consoles, plotting contacts, confirming tracks, speaking in clipped, practiced phrases. In the passageways, supply carts rattle, tie-down chains scrape, boots strike steel ladders, and the daily machinery of a working fleet continues, even while the larger choreography unfolds beyond the skin of the ship. RIMPAC's official focus includes interoperability, missile proficiency, anti-submarine warfare, and mine clearance. Those are not decorative training categories. They are hard maritime problems. Missile work tests timing, queuing, and confidence under compressed decisions. Anti-submarine warfare demands patience, acoustic discipline, and shared awareness across ships and aircraft. Mine clearance calls for precision, caution, and the ability to make dangerous water usable again. Each mission says something about the future battle network. A modern fleet is not only judged by how much firepower it can bring, it is judged by how well it can sense, share, classify, and act before confusion outruns command. That is where the unmanned story begins to merge with the Allied story. If the Navy wants more mass more quickly, and if it wants that mass spread across wider distances, then the network connecting the force becomes even more important. Smaller unmanned vessels may extend presence, increase scouting reach, or carry modular payloads, but only if they can fit into a larger operational picture. A ship that cannot be integrated is not a true addition to fleet power. It is only another object at sea. Recent Navy moves suggest that this integration is no longer a side experiment. In April 2026, the service established Unmanned Surface Vessel Squadron 7 with a mission tied to robotic autonomous systems and to operations in bandwidth, limited or denied environments. That detail matters more than it may first appear. It implies the Navy understands the future network cannot assume perfect communications. It cannot assume every node will always remain connected. It must function when the signal weakens, when distance stretches timing, and when a force has to keep moving with incomplete information. That is a sobering idea, because for years the language of advanced warfare often sounded frictionless, as if sensors would always see, networks would always connect, and data would always arrive in time. Real naval operations are harsher than that. Sea state interferes. Weather closes in. Equipment fails. Distance imposes delay. Adversaries contest the spectrum. Commanders do not get to choose only favorable conditions. So when the Navy organizes an unmanned squadron with denied environments in mind, it is admitting a simple truth. The battle network of the future must be resilient, not merely impressive. A visual beat here can stay grounded and practical. Show an unmanned surface vessel riding uneven water, its low hull lifting and settling through chop. Cut to a control station where operators monitor feeds, check link status, and track system health on plain, functional displays. Then back to topside footage, antennas against a pale sky, salt spray catching on camera glass, line handlers on a nearby support vessel, a rigid hull boat crossing the wake. Nothing secret is required. The story is visible in the rhythm of operation itself. Machines extend presence, but people still frame the mission, supervise the system, and absorb the burden when conditions turn difficult. The alliance dimension appears clearly in the high north as well. During Arctic Century 2026, the U.S. Navy operated unmanned systems with Norway in missions tied to maritime domain awareness, mine countermeasures, and the protection of undersea infrastructure. That matters because it shows unmanned operations are not only being tested in theory or in isolation. They are being worked into bilateral cooperation in a demanding environment for missions that are both practical and strategically sensitive. Cold water, austere conditions, and long distances do not simplify naval experimentation. They expose whether concepts are robust enough to travel. The larger meaning is that Allied operations are becoming a proving ground for networked maritime warfare. If one nation brings a crewed combatant, another contributes local knowledge, another adds aircraft, and unmanned systems extend surveillance or reconnaissance, then the force becomes more than the sum of national inventories. It becomes a distributed web of observation and response. But that web has to be rehearsed. It has to be built through repeated contact, shared procedures, and clear expectations. Trust at sea is operational, not rhetorical. Reporting around the Navy's future force has pushed this idea even further, describing plans to deploy thousands of smaller unmanned surface vessels to the Indo-Pacific by 2030, alongside a smaller number of medium unmanned surface vessels integrated with larger formations. Even if the exact path remains uncertain, the direction is revealing. The Navy appears to be thinking in layers: larger crewed ships for endurance and command, medium unmanned vessels for payload and range, and many smaller craft to add presence, complexity, and what some leaders have framed as risk-worthy mass. That phrase captures a major shift in thinking. A one-size-fits-all fleet is too rigid for the scale of modern maritime competition. A future force built around a mix of platforms, robotic systems, and modular payloads accepts that not every mission requires the same ship, and not every risk should be borne by the same kind of crewed vessel. It is an attempt to build volume without waiting for every answer to emerge from the oldest and slowest acquisition pathways. It is also an attempt to distribute the force so widely that an opponent faces not one clean target set, but a broad and adaptive pattern. Still, this future battle network is not just a theory of machines, it is a theory of coordination. Medium unmanned surface vessel reporting has described requirements such as substantial range, meaningful speed, operation in sea state 4, and payload capacity for modular use. Whether every target is achieved on time remains to be seen. What matters for this chapter is the logic behind it. These are not being imagined as decorative test craft. They are being shaped as working participants in fleet operations, vessels expected to move over distance, carry useful loads, and contribute in real maritime conditions. That, in turn, loops back to shipbuilding. The industrial debate in 2026 increasingly links unmanned systems to a broader high-low fleet and modular strategy. In plain terms, the Navy is searching for ways to add capability without relying entirely on the slow production of large, exquisite ships. That does not remove the need for major warships, it changes the architecture around them. The future fleet may depend on whether shipyards, suppliers, and procurement teams can support a more distributed ecosystem rather than a narrower list of traditional hulls. And so the Allied network becomes part of the industrial answer as well. Exercises like RIMPAC test the operational concept that industry is being asked to support. They ask whether a mixed force can actually perform the missions planners describe. Can crewed and uncrewed vessels contribute to a common picture? Can fleets from many nations coordinate missile defense, submarine tracking, mine work, and patrol coverage in a way that creates real combat value? Can logistics keep enough of that force moving across oceanic distance? These are not separate questions. They are one question seen from different angles. The footage can stay close to that human reality. Forklifts move pallets across a pier. Fuel hoses are connected and disconnected. Sailors inspect equipment lockers, secure lines, wipe salt from fittings, and log maintenance checks in cramped workspaces. In a flag plot or command room, screens fill with symbols while officers compare reports from ships, aircraft, and remote systems. On the bridge, the sea state shifts, wind rises, and a formation subtly adjusts. The future battle network is often described in abstract language, but it lives or dies in these ordinary motions of labor, discipline, and repetition. So Chapter 8 does not end with a simple promise that technology or alliances will solve everything. It ends with a harder conclusion. America may not build its way to advantage through large ships alone. It may need a coalition-ready fleet built from many layers, linked by a network that can survive friction, distance, and disruption. RIMPAC suggests the scale of that ambition. Arctic cooperation suggests its widening geography. New unmanned squadrons suggest the Navy is trying to institutionalize the change, and the wider shipbuilding debate suggests that mass, modularity, and integration are becoming parts of the same strategic sentence. The future battle network, then, is not a single device and not a single program. It is a habit of operating. It is the ability of allied crews, command teams, aircraft, submarines, unmanned vessels, and logistics chains to function as a connected maritime organism. If America can build that kind of fleet and build it quickly enough, then ship count alone may stop being the only measure that matters. If it cannot, then even a larger fleet may remain slower, more brittle, and less coherent than the future demands. And so the question at the end is not only whether America can build more ships, it is whether it can build a fleet that keeps learning after each ship leaves the pier. On screen, the image can begin with a gray morning on a working waterfront. A hull sits alongside the pier, lines pulling gently against the tide. Forklifts move pallets under a crane. Sailors step across a wet deck in cranials and float coats. A maintenance team checks fittings at a crew station. Nothing in the frame is dramatic. That is the point. Naval power is not only made in launch ceremonies. It is made in repetition, in logistics motion, in crews learning where each cable runs, in teams solving small problems before they become strategic ones. This is where the fleet after the ship begins. For much of modern naval history, the ship itself has been treated as the final answer. Build enough destroyers, enough submarines, enough support vessels, and the logic seems complete. But the current debate suggests something more demanding. A fleet is not only a collection of hulls, It is a system that must sense, move, decide, repair, distribute, and adapt across wide distances. In that system, the ship is essential, but it is no longer sufficient by itself. That is one reason the Navy's recent unmanned efforts matter beyond their small size. In May 2026, the service announced 7 companies selected for medium unmanned surface vessel marketplace at sea demonstrations. The structure of that effort matters as much as the hardware. The program uses a prototype path with a success incentive tied to performance at sea. That is a different signal from a long, sealed process that discovers weaknesses only after years have passed. It suggests the Navy trying to learn faster, test faster, and shift more technical risk toward real demonstration instead of paper certainty. A good visual beat here is a low, steady shot along the side of a smaller unmanned craft as it rocks lightly in harbor chop. Then cut to a console in a command room. Screens glow in darkened light. A watchstander leans forward in a headset. The camera does not need to show sensitive details. It only needs to show that the fleet's future may depend on the relationship between steel and the water, and decisions made through networks, sensors, and control stations, often far from the bridge wing of a traditional warship. That relationship is already being exercised. In Arctic Century 2026, the Navy operated unmanned systems with Norway in a bilateral setting tied to mine countermeasures, maritime domain awareness, and the protection of undersea infrastructure. Those are practical missions in hard water, not abstract concepts. The High North is not a forgiving place to test ideas. Sea state, distance, cold, and uncertainty strip away slogans very quickly. If systems can contribute there, in alliance conditions, they are doing more than serving as technology demonstrations. They are entering the habits of coalition operations. That matters because no Pacific or Atlantic problem will be solved by one service staring inward. RIMPAC-scale 2026 is set to bring together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. Numbers like these do not guarantee effectiveness, but they reveal scale. A modern fleet has to function inside coalition geometry. It must pass information, align procedures, and fight within shared timing. The fleet after the ship is therefore also the fleet after solitude. It is a force designed not only to sail, but to connect. Visually, this is where the chapter can widen. Show a helicopter deck during replenishment preparations. Show signal lamps at dusk. Show aircraft parked on a flight line. Show a destroyer cutting through a moderate sea state, then cut to a foreign partnership on station nearby, then back inside to a plotting room or operations center, where officers and enlisted watch teams manage tracks, reports, and tasking. The rhythm should feel deliberate. The audience should sense that naval power is built from coordination as much as from tonnage. Another sign of this shift is organizational. In April 2026, Unmanned Surface Vessel Squadron 7 was established with an explicit role in operating robotic autonomous systems in bandwidth-limited or denied environments. That phrase is easy to overlook, but it may be one of the most revealing in the entire discussion. It implies that the Navy is not assuming perfect connectivity. It is preparing for degraded conditions, contested conditions, and moments when autonomous or semi-autonomous systems must still contribute despite friction. That is not simply procurement. That is fleet design expressed in organization. If the fleet is being reorganized around distributed systems, then speed in shipbuilding cannot mean only speed in welding or launch schedules. It also has to mean speed and integration. Can new systems arrive and enter useful service without years of delay? Can crews train on them in a way that is durable? Can support systems keep them running? Can doctrine absorb what the machines are good at and reject what they are not? A Navy can buy quickly and still fail slowly if these questions are left unanswered. Some reporting this spring has pushed the scale of this idea even further. USNI reported that the Navy plans to deploy thousands of smaller unmanned surface vessels into the Indo-Pacific by 2030, alongside a force of more than 30 medium unmanned surface vessels. Separately, USNI reported prototype MUSV requirements around range, speed, sea state performance, and payload that suggests serious operational intent rather than novelty for its own sake. These details come from defense analysis reporting rather than a final official promise, so they should be understood as indicators of direction. But even as indicators, they are important. They point toward a fleet architecture where large combatants do not disappear, but stop carrying every burden alone. A visual sequence here can stay grounded. Show containerized equipment being craned onto a pier. Show a technician securing cables on a compact deck. Show spray coming across the bow of a smaller craft in a manageable but real sea. Show an engineering watchstander inspecting a machinery space ladder well on a conventional ship. Then, cut to a logistics chain. Pallets, tool cases, spare parts, line handlers, fuel hoses, and the quiet choreography of resupply. The meaning is simple. If mass is to become real, it must be maintained. If distribution is to become real, it must be maintained. If distribution is to become real, it must be supplied. Senior Navy leadership has also used language that marks a conceptual break with older assumptions. One reported framing described a future hedge force built around risk-worthy mass and robotic autonomous systems, rather than a one-size-fits-all fleet design. That idea does not reject capital ships. It challenges the belief that every mission must be carried by the same type of expensive platform. In strategic terms, it asks whether quantity, modularity, and adaptation can create resilience, where exquisite concentration may create brittleness. And this is where the industrial base returns to the center of the story. The broader 2026 shipbuilding debate links unmanned systems to a high-low mix and to a more modular approach across the industrial base. That does not make the old shipyards irrelevant. In fact, it may make them more important. A Navy that mixes major combatants with distributed unmanned systems still needs yards, suppliers, skilled labor, repair capacity, and procurement discipline. The lesson is not that software replaces shipbuilding. The lesson is that shipbuilding now sits inside a wider production ecosystem. That ecosystem is easy to romanticize and hard to rebuild. You can show that visually without exaggeration. Let the camera linger on welding arcs inside a fabrication space. Show stacks of plate. Show a sailor tracing a checklist on a clipboard near a damage control station. Show a crane hook swinging over a key. Show fuel, hoses, stores, and weathered non-skid underboots. A Navy is not an idea floating above material reality. It is a chain of labor, timing, maintenance, and institutional memory. Every delay in one link travels outward. So when we ask whether America can still build a Navy fast enough, the sharpest answer may be that the challenge is now split in two. First, can it still produce ships, systems, and crews with enough speed to matter? Second, can it shape those pieces into a fleet that remains coherent under pressure? The first question is industrial. The second is organizational, doctrinal, and operational. A Navy that solves only one of them will still arrive incomplete. The closing images should carry that thought. A ship gets underway. Tugs peel away. Sailors stand at stations on the weather deck. The camera moves from the wake to the bridge windows, then inside to a command space, then out again to the open sea. Nearby, smaller craft move against the same water. Somewhere else, Allied ships prepared to join an exercise. Somewhere farther north, unmanned systems patrol cold approaches. At a pier, more equipment is loaded for another run. The work never ends at launch. It begins again there. Because the fleet after the ship is really the test after the ceremony. It is the trial after the contract award. It is the watch after the briefing. It is the ability to combine large ships, smaller systems, coalition partners, industrial capacity, and trained people into something that can absorb shock and continue to function. If the Navy can do that, then the future fleet may be judged by more than how many gray hulls it can count. It may be judged by how quickly it can learn, how widely it can distribute risk, and how steadily it can keep operating when the easy assumptions fail. If it cannot, then every launch will remain only a partial success. The ship will be real, but the fleet behind it will still be